In this video, we want to do a little bit of review on balancing chemical equations, as well as kind of showing you a quick and pretty straightforward technique to make sure your equations are balanced. So the way we're going to do this, we're just going to go through 3 different examples using this technique of balancing equations. The first one's going to be relatively straightforward, and it involves this reaction. N2 plus H2 forming NH3. So in this reaction right now, this is not balanced. We can tell that it's not balanced if we just quickly kind of count up the numbers and types of each element on each side. We can treat the reaction arrow kind of in the same way you would a mathematical equal sign in some senses, where what's on the left versus what's on the right may look different but still have to have some numerical equivalency. So if we look at this right now, I have 2 nitrogens on the left, only 1 on the right. 2 hydrogens on the right, 3 on the left. It looks like we are losing a nitrogen and adding a hydrogen, or maybe a nitrogen becoming a hydrogen. None of those things are actually happening in this. So we have to make sure we balance the chemical equation. Chemical equations have to follow law of conservation of mass and matter. We can't create or destroy things in this. We can change forms, we can change the way things are connected, but we can't create or destroy in this process. So when we're looking at this, there's a couple things we could try to maybe do to make this balanced. Maybe I could change some of these subscripts to make that balanced. Well, I could do that and it would balance it, but it would change the equation. If I change any subscript for any element that I see, I no longer have the same reaction that I started with. I formed a different reaction. So that's not how we can balance this equation. We can't be changing the subscripts. So we can't change the identity of what these elements and these molecules and compounds are. But what we can end up changing, though, is the relative amounts of each. And that's what we're going to end up doing. What we can do is we can change these numbers that are sometimes put out in front of our compounds. These we sometimes call coefficients. And coefficients work a little bit differently than subscripts do. Coefficients apply to everything that came after it. Coefficient applies to what came after it. The coefficient that we would use here would apply to what comes everything after it. Meanwhile, subscripts just apply to what is immediately before. So when we think about a reaction, we sometimes call the left-hand side the reactant side, and the right-hand side the product side. So I want to show you a real quick technique that just involves some real quick tallying up of things that will help you to easily balance these equations. So it really is a tally sheet. Reactants and products, or left and right. And all I'm going to do is I'm going to start with what elements I have in play. This one's relatively simple. I only have 2 elements, nitrogen and hydrogen. And I'm just going to start listing where I'm currently at. On the reactant side, I have 2 nitrogens right now. On the product side, 2 hydrogens. On the product side, 1 nitrogen, 3 hydrogens. So if we quickly just recount, reactant side, 2 nitrogens, 2 hydrogens. Product side, 1 nitrogen, 3 hydrogens. Again, we can see we're not balanced. Now, in this case, it doesn't matter which element you start with in terms of trying to balance it, but we're going to change coefficients to balance these equations. So let's just start with the nitrogen. I have 2 on the reactant side, 1 on the product side. How can I fix that? Well, I can fix that by changing the coefficient on the product side to 2. Now that's going to do a couple things. It's going to change the amount of nitrogen I have to 2. It's also going to change the amount of hydrogen I have, though. So I have 2 of these things. Each unit has 3 hydrogens. Now I have 2 of them. So I'm going to have 6 hydrogen now. So now that I fixed the nitrogen, now I can work on the hydrogen. 2 on the reactant side, 6 on the product side. I can change that by placing a 3 for a coefficient in front of the hydrogen. That's going to change the amount of hydrogen to 6. Now, if you're careful and methodical and don't rush, you should be able to quickly check yourself and make sure you did it right. And I recommend always doing this when you're balancing an equation. Just quickly go back and look to see how you've done. 2 nitrogen, 2 nitrogen. 6 hydrogen, 6 hydrogen. 2 nitrogen, 2 nitrogen. 6 hydrogen, 6 hydrogen. So I did my counting correctly. Now I'm just making sure reactant and product sides match. Nitrogen matches 2 on each. Hydrogen matches 6 on each. When everything looks good, you've correctly balanced this equation. Now this one was pretty straightforward. The next one I want to do is a little bit more involved. So the next one I want to do, a little bit different reaction. Next one I want to do is I want to do this equation. C3H8, you're probably most familiar with that. That's the propane fuel that you have in your grill. Propane, we know, reacts with oxygen. It's flammable. That's where we're getting the heat source for this. And this ends up producing carbon dioxide as well as water coming out of this. So again, we're going to use the same technique we did in the previous problem. Reactants, products. Here I have carbon, hydrogen, and oxygen all in play. And right away, I'm just going to take a real quick accounting of where I currently stand. On the reactant side, 3 carbons, 8 hydrogens, 2 oxygens. On the product side, 1 carbon, 2 hydrogens, 2 and 1, 3 oxygens on the product side. So now I need to start balancing. But here it really matters what I choose to start with, or what I don't choose to start with. You have to make good choices in order to keep these relatively straightforward in order to balance. And here's how you make good choices. You look at your reaction and you want to start with elements that appear in the least number of locations. Not how many we have. That's not what we're talking about. Least number of locations. So let's kind of look at this. Carbon appears in 1 location on the reactant, 1 location on the product. Hydrogen, 1 location in the reactant, 1 location in the product. Oxygen, though, appears in 1 location on the reactants, but 2 locations on the products. So oxygen appears in the most number of locations. When you see something that's appearing in a lot of different locations, that's your signal, that's your clue to definitely not start with that one. You want to save that one till the end. Instead, you want to start with the things that appear in the least number of locations. So for us, that would be either carbon or hydrogen. We're just going to go ahead and start with the carbon on this one. 3 carbons, 1 carbon. Can I fix that? I can definitely fix that. I can put a 3 subscript out here to give me my 3 carbons. But by doing that, I'm also going to change the number of oxygens that I'm looking at. Now I have 6 plus 1. I change the number of oxygens now to 7. Now, even though I'm not really focusing on the oxygens yet, I'm still adjusting my tally to reflect that. I'm still going to leave those alone for the time being because that appears in the most number of locations. Now I'm going to adjust the hydrogens, saving the oxygens till the end. 8 hydrogens on the reactant side, 2 on the product side. Can I fix that? I can fix that. I can fix that by making this coefficient a 4. So now that's going to change the number of hydrogens to 8. It will also affect the number of oxygens I need to keep track of. 6 and 4 now make 10. Now that I've taken care of the carbons and the hydrogens, it's now time to deal with the oxygen. Remember, I saved the oxygen till the very end because it appeared in the most different number of locations. 2 on the reactant side, 10 on the product side. I can fix that. How can I fix that? I can fix that with a 5 out here. That's going to change the number of oxygens that I'm dealing with to 10. Now, again, do a quick double check. It doesn't take that long to recount things and make sure you did this correctly. It's going to recount everything we did. 3 carbons, 3 carbons. 8 hydrogen, 8 hydrogen. 5 times 2, 10 oxygens, 10 oxygens. On the product side, 3 carbons, 4 times 2, 8 hydrogens. 3 times 2 is 6, plus 4 times 1, 6 and 4 make 10 oxygens. So I did the math right. Does everything match? Reactants and products? It does. So this is the correct balanced equation. Now, could you have gotten here by starting with the oxygen instead of saving it to the end? Yes. But it would take you far, far, far longer, and you would have to spend much more time and effort in order to balance this, because then you would be kind of randomly changing some of these. You always want to make a good decision on where to start or where not to start. You want to start with the things that appear in the fewest number of different locations. Save those things that appear in the most number of locations till the very end. We have one more example that we want to do. Everything's balanced, everything checks out, we did our math right, this one's good. We have one more that we want to do here. And it's similar to the last one, but it adds that last piece that you sometimes have to do when you're balancing equations. So this one is similar, except this is C4H10 plus O2, producing still CO2 and water. We're going to use the same exact technique that we used in the previous one. We're just going to make a tally sheet. So if I make my tally sheet, reactants and products, here I have again carbon, hydrogen, oxygen, carbon, hydrogen, oxygen. And make a really quick tally to see where we're at. Well, 4 carbons, 10 hydrogen, 2 oxygen on the reactant side. On the product side, I'm looking at 1 carbon, 2 hydrogen, 3 oxygen. Same logic as we used in the last problem. The element that appears in the most number of different locations, save that one till the end. In this case, it's going to be oxygen again. Doesn't matter whether we start with the carbon or the hydrogen. So just to show that it doesn't really matter where we start, this time let's start with the hydrogen. 10 hydrogens on the reactant side, 2 on the product side. Can I fix that? Yes, I could put a 5 out here for the hydrogen. That's going to change the amount of hydrogen I'm dealing with to 10. It's also going to change the amount of oxygen I have, though. Now I have 5 plus 2 still. Now I'm going to have 7 oxygen. Now let's take care of the carbon. 4 carbon on the reactant side, 1 on the product side. I can fix that with a 4. That's going to change the amount of carbon I have to 4, but it will also at the same time change the amount of oxygen that I have. 8 and 5 make 13. So now I'm ready to deal with the oxygen. So if I'm dealing with the oxygen, I have 13 on the product side, 2 on the reactant side. So I'm looking at this and I'm seeing a little bit of a problem. If I try 6, I'm not going to get enough oxygen. If I try 7, I'm going to have too many oxygen. But mathematically, what would be the correct number in order to give me the correct number of oxygens? Well, if 6 is too few and 7 is too many, what about 6.5? 6.5 times 2 would give me 13. So I can try 6.5 here. And 6.5 would give me 13. So that looks like it's going to work. And it does work mathematically. Mathematically, this is fine. But chemically, this is not fine yet. In these balanced equations, you cannot have a decimal or a fraction. The reason you can't have a decimal or a fraction is that this reaction can be read in molecule amounts. There's no such thing as half a molecule, or a quarter of a molecule, or 2/3 of a molecule. 0.5 molecules doesn't mean anything. Molecules only come in whole amounts. So even though this mathematically makes sense, chemically this doesn't make sense yet. I can't leave fractions or decimals here, even if that does make the math correctly. Well, if I can't leave a decimal or fraction here, how can I get rid of that? Well, anytime you have a half, how do you get rid of a half? Well, you could get rid of a half to make a whole number by doubling that. But if I double this, I'm going to have to double everything. So what you essentially do to get rid of that half is you take the entire equation and multiply it through by 2. Now we don't leave it like this, we actually show what happens with this. So I'm going to distribute this 2 into all of the different coefficients. So when I do that, what am I going to have? 2 times 1 is 2. 2 times 6.5 really makes 13. 2 times 4 make 8. 2 times 5 make 10. So I went and I distributed that 2 into all the coefficients. Now I just made a bunch of changes. We think it's right, but there's no reason not to be sure that it's right. Quickly just go back and double check everything. There's no reason to not have a successfully balanced equation because it's real easy to check. Things either match up or they don't. If they match up, you did it correctly. If they don't, it's not correct. So let's retotal everything. Carbons on the reactant side, 2 times 4 make 8. Hydrogen, 2 times 10 make 20. Oxygen, 13 times 2 make 26. On the product side, carbons, 8 times 1 make 8. Hydrogen, 10 times 2 make 20. Oxygens, 8 times 2 make 16 here. 10 times 1 make 10 here. 16 and 10 is going to make 26, so I double checked our math. Now, does everything match up? 8 carbons, yes. 20 hydrogens, yes. 26 oxygens, yes. So you can temporarily use a decimal or a fraction as kind of a placeholder to kind of see how things are going to need to be balanced. But at the end, you need to get rid of that fraction or decimal. You can't leave a fraction or a decimal in there. Strongly encourage you just to kind of use the tally technique. There's other ways of balancing these, but this just gives you a real quick, you can always look and see where you're at and what you still need to do. And this will work for all the different things that you might have to balance.